Hello, welcome to the first part of section 8.6, representing functions as power series. This is very useful, especially when we're trying to compute the integral of a function and it doesn't have an antiderivative, or if you want to solve differential equations. So it's very useful. Okay, let me start by reminding you that if you take a geometric series, right, then given that the absolute value of x is less than 1, then it'll be equal to 1 over 1 minus x, in this case in particular. Now, usually, again, and I know I already said this, usually we start our geometric series at 1, okay, but now we're starting at 0 so that we can take care of that constant, and we want the exponent to be the same as the n, okay? That is it. So this is what we usually call r. Now, we're going to use this information. We're going to use the fact that we know the convergence of a geometric series to express a bunch of different functions as power series, okay? So example 1, we have to express 1 over 1 plus x squared as a power series, and we have to find the interval of convergence, okay? So the very first thing I'm going to do is I'm going to notice that if I have 1 over 1 plus x squared, I can rewrite this as, well, 1 over 1 minus negative x squared, okay? Right? Now, by doing so, I know that then this will be my r, right? This is what we usually write as r. So let me write it. Let me just make a little note here. This is our r. So when I go back and write it as a geometric series, I write it as a sum, then this is just equal to, well, I'm going to start at n equals 0 all the way to infinity, and I take my r and I put it to the nth power, okay? This is what we have, okay? Now, from here, we can use our theory of geometric series theory to know the interval of convergence, okay? So again, since this is my r, then I know that this converges, right, whenever the absolute value of negative x squared is less than 1. Now, having the absolute value of negative x squared being less than 1 is the same as saying I can take that, this is just the negative absolute value of negative 1 times the absolute value of x squared less than 1. This guy, it's equal to 1, so forget about it. And now we know that if the absolute value of x squared is less than 1, then x squared is less than 1 larger than negative 1, and this is the case if and only if x is in between negative 1 and 1, okay? So this does not affect our interval of convergence, okay? Now, and you also know that since this is a geometric series, it does not converge at the endpoints. This is the interval of convergence. You know that. Now, if you want to write it as a power series, right? If I want to turn this and write it as a power series, I have to have something in terms of n times my x to the exponent. Okay. Recall that whenever we have a power series, we have something from n equal to 0 to infinity, cn, and then x to the n, okay? That's what we're shooting for here. So I'm going to do it real quick. I have here that this is equal to the sum from n equals 0 to infinity of, well, negative 1 to the n, and then x to the 2n, okay? Now, this is my power series, right? This is 1 over 1 plus x squared written as a power series. Okay, perfect. What else do we have? Let's do another example here. Find a power series representation of 1 over 2x plus 5, and again, find the interval of convergence. And then again, we're going to do exactly the same steps, okay? I'm going to start by realizing that I have that this is 1 over 2x plus 5, and I want to write it as 1 over, right? 1 over 1 minus something, okay? That's my goal. Now, in order to do that, I'm going to have to factor out a 5. If I factor out 5 in the denominator, then my first term becomes, 2 over 5x plus 1. And you can always check that this is correct by multiplying, right, by multiplying 5 times this, okay? So 5 times 2 over 5x, cancel 5, you get 2x. 5 times 1, you get 5, then this is good. Now, let me write it so that it looks like what we're used to. This is 1 over 5, and then we have 1 plus 2 over 5x. Now, if I do that, then this is just 1 over 5 times 1 over 1 minus, and then negative 2 over 5 x. Okay, so now this is starting to look more like the convergence, right? The actual limit of a geometric series, okay? So now in this case, this will be my r. So I can rewrite this as, well, 1 over 5 times the sum from n equals 0 to infinity of negative 2 over 5x to the n. And then again, from here, I know the convergence. From here, I know that this converges given the fact that the absolute value of negative 2 over 5x has to be less than 1. This comes again from the geometric series. Therefore, if I take the absolute value of the negative 2 over 5, I get that this is 2 over 5 absolute value of x less than 1. Well, that tells me that the absolute value of x is less than 5 over 2, okay? Therefore, this gives me that the radius of convergence, my radius of convergence is equal to 5 over 2. And I also know that the interval of convergence, IOC, is, well, negative 5 over 2 less than x less than 5 over 2. Okay, now this part is solving this part of the problem, right? Find the interval of convergence. Now we still have to finish the part where we find a power series representation. So we have to manipulate this expression a little bit more, okay? A little bit more. So 1 over 5, sum from n equals 0 to infinity. And then here I have negative 2 over, actually I'm going to write it as, let me just do it, negative 1 to the n, and then 2 to the n, and then x to the n over 5 to the n, okay? I'm just splitting, right? I'm just distributing that n. And then I get that this is 1 over 5, n equals 0 to infinity. And then again, I want to have it like something that depends on n times x to the n. So I'm going to put this 5 inside. If I do so, I get that, let's see, this is negative 1 to the n, 2 to the n, x to the n, all over, I had 5 to the n times the other 5, I get 5 to the n plus 1, and this is my power series representation of 1 over 2x plus 5. I have one last example in this part of section 8.6. Find a power series representation for x cubed over 2x plus 5. And then again, we have to find the interval of convergence, right? We have two separate problems here. First one, I'm going to do exactly the same thing we did before. I'm going to take x cubed over 2x plus 5 and write it as, well, I'm going to write it as x cubed times 1 plus 2 over 5x. And hopefully you're looking at this and recognizes that this is from example 2. We know that this is just equal to x cubed times the sum from n equals 0 to infinity of the power series representation we got in example 2, which is negative 1 to the n, 2 to the n, x to the n over 5 to the n plus 1. Bring this x cubed inside, and we get that this is just the sum from n equals 0 to infinity, negative 1 to the n, 2 to the n over 5n plus 1, x to the n plus 3. Okay, that's it. That is my power series representation of x cubed over 2x plus 5. And then we know that it converges for exactly the same values of x. So we know that this is the case again if we have that the absolute value of x is less than 5 over 2. Again, that tells me that this is my radius of convergence, and my interval of convergence is given by the numbers in between negative 5 over 2 and 5 over 2. And one more time, we're dealing with geometric series. We know that they do not converge on the endpoints, okay? That's all I have for this first part of section 8.6. Stay tuned. There's one more comment. Bye-bye.